Hi there. After seeing how we can describe a traveling wave through a medium, we can ask about the motion of the particles that constitute the medium itself. If a transverse wave propagates at a speed v, let's say in the x direction, then the particles of the medium oscillate in the y direction. The speed of the wave is the speed at which the perturbation travels along x. But the particles of the medium oscillate and follow a harmonic motion. Therefore, they have an acceleration. If we take the equation that describes the wave, this is an equation that tells the height y as a function of time and as a function of position x. So if we want to calculate the velocity of the molecules of the material medium, what we actually want is to see the rate of change of y as a function of time. This means that for a given position x, what is the derivative of y as a function of time? We calculate the partial derivative of y as a function of time. So v sub y is equal to minus vy max, the maximum speed, times the cosine of omega t plus phi. The maximum velocity of the molecules of the medium is vy max, omega a. Look that this is not the speed of propagation of the wave. This is the velocity of the molecules of the material medium. How fast they are oscillating up and down. We can do the same for the acceleration, the partial derivative of v with respect to time. Minus a y max times the sine of omega t plus phi. Look that the acceleration is not constant. Although this is no surprise, as we know that the particles oscillate and acceleration points are alternatively up and down. This acceleration changes sinusoidally, so it is the acceleration of a simple harmonic oscillator. Look that these velocity and acceleration are perpendicular to the motion of the wave. This is so because we are describing a transverse wave. If a longitudinal wave, then the oscillations would also be in the x direction. So, we have studied the change in time of the medium for a given position. Let's now explore the change in position for a given instant of time. I will do the partial derivative of y with respect to x, keeping time constant. This gives me the slope of the wave. This slope also changes sinusoidally, as can be seen in the shape of the wave. I will take the second partial derivative with respect to x. Now let me play a little bit with these results. I will divide this second derivative by this other second derivative. This here is the linear wave equation. This is a relationship between the velocity of the propagating wave and the dependence of the wave with respect to time and to the axis of propagation. It is a general equation for traveling waves. As a matter of fact, this equation is valid no matter the shape of the wave, so long as f of x is equal to f of x plus or minus vt. So for any periodic wave, this equation is a consequence of the linear response of the medium to the perturbation due to the traveling wave. The fact that it is a linear relation has a consequence the fact that the effect of two propagating waves is the sum of the effects of each one of the waves. One example of a one-dimensional mechanical transverse wave is a wave on a rope. Consider the equation for a traveling wave on a rope as y1 equals to a sine of k1x minus omega 1t. This corresponds to a wave of amplitude a propagating to the right with frequency omega. The initial conditions indicates that the perturbation at the origin was 0 when t was equal to 0. Consider now a second wave of the same amplitude, this one propagating to the left at twice its frequency. The speed of propagation will be the same for both, v equals to omega over k. Because omega 2 is 2 times omega 1, then k2 is also 2 times k1. Then y2 equals to a times sine of k2x plus omega 2t. That can be written as a times sine of 2k1x plus 2 omega 1t. Let's prove that the sum of both waves satisfies the linear wave equation. The sum equation is the second derivative with respect to the position is the second derivative with respect to time is because v is omega over k. This result manifests the superposition principle. May science be with you.